In the last lecture, we covered classification metrics and decision trees. So let's take a quick look at the past lecture materials. We looked at the precision versus recall trade-off. And next, we also looked at how to actually determine an F1 score, which was a precision multiplied by recall, which sort of balanced the two differing metrics, sort of competing metrics. And then we looked at the ROC curve. And I didn't get a chance to go into detail about the ROC curve last time due to shortage of time. So I'm going to spend some time on this curve today because it is an important curve and it sort of summarizes, it's a very practical way of being able to determine the various the evaluation between various kinds of algorithms. So we'll take a look at this in detail today. And we looked at examples of different classifications. Then we covered decision trees. And we looked at several examples of decision trees. And we looked at the Gini, calculation of the Gini impurity measure. And we looked at couple of examples of that. And finally, we looked at something called ensembling. And as I mentioned, ensembling is a general technique. In this particular case, ensembling is being applied to decision trees. And decision trees, essentially, when they're ensembled together or combined together, they're called random forests. And this was a technique which we saw that it has a number of advantages and some disadvantages as compared to decision trees as well. So now let me see what time it is, just to make sure that in case I'm running over your quiz, please do stop me a couple of minutes beforehand. So let's take a look at the ROC curve. Now, let's take the decision threshold. I'm going to show you different extremes of the decision threshold. So here's the decision threshold, which is being shifted all the way to the left. Okay, so this is a similar example to what you've already seen, which had 6 rectangles and 4 triangles. And we have the confusion matrix over here. And basically, we're looking at a decision threshold A, where we've shifted the decision all the way to the extreme to the left. And we're looking at predictions for rectangles, okay? And so let's do a little bit of a quick calculation, and I need your help for this. So what would be the true positive rate versus the false positive rate? Remember that in the ROC curve, we basically plotting the true positive rate versus the false positive rate. And these are the equations for this. The TPR is essentially the recall, and FPR is slightly different. As I mentioned last time, it's a slightly different metric. But basically, the true positive rate is basically looking at true positives divided by true positives plus false negatives. And false positive rate is simply looking at the false positive as compared to the true negatives. Okay, so you can see that this is sort of vertically aligned. So can somebody tell me what the answer here would be for threshold A? What would be the number of true positives?
Sir, true positives will be 4.
True positives would be how many? I'm sorry, speak up a little bit.
Sir, 4 होने चाहिए 4 क्योंकि triangles के portion में है ना हम लोग.
No, we're looking at rectangles. Okay.
Rectangles.
Yeah.
6.
So now the decision threshold is this. So in other words, everything over here is being considered as positive, and everything to the right of this line is being considered as negative.
Negative.
0.
So 0. Yeah. So there are 0 positives and 0 plus. Now, how many false negatives are there?
False.
6.
So false negatives would be 1, 2, 3, 4, 5, 6. All rectangles are considered over here. So this would be 0. And what about a false positive rate? So false positives.
So false
4.
positive is zero है.
So are there any positives?
No sir.
So again, there are no false positives.
4.
See, positives are everything that is on the left side of this decision threshold, okay? And everything on the right side of it is a negative. So as you can see, both false positives and both true positives and false positives are actually zero over here, okay? Nothing has been considered. It's an extreme case of the decision threshold. So you can see that both the false positives is also zero, okay? And so this will be zero. And how many true negatives are there?
4.
Yeah, so there'll be 4 true negatives. So in other words, this will also be zero. So now if we try to plot the true positive rate versus the false positive rate, where do you think on this curve will this A appear? Will it be over here? Will it be here? Will it be here? Will it be here?
Origin.
It'll be at the origin, right? So that's very clear. So this is the first point, is that we've got this particular point. When the decision threshold is at this extreme, the point on the curve is right over here, okay? Now, similarly, let's take the other extreme, and I'm going to call it decision threshold D. Now, here we've... Sorry? So I think we've got some time left. So here, let's take a look at this case. Now, for decision threshold D, what will be the true positive rate? So how many true positives are there?
6.
Right, so there are 6 because all the rectangles are actually true positives. So 6 divided by 6 plus, and how many false negatives are there? How many negatives are there on this side?
0.
0, right?
Zero.
So this is going to be 1.0. And what about the false positive rate? False positive saying how many false positives are there?
4.
4 and 4. And how many true negatives are there?
0.
True. So this is also 1.0. So if you plot this, where is this going to be? So point A was here, and D is going to be over here, right? Because it's both 1 and 1 over here. Both the rates are here. So you can see that as you move the decision threshold from one extreme to the other, you go from one point to the other extreme. Okay. And now the question is, as you're moving this decision threshold, do you go like this? Do you go straight? Do you go down? Which way do you go? Okay, and that will depend on the specific scenario, but it will always start and end at these two extremes. Okay. Now, let's take a couple of additional points. Okay, so I'm going to take a decision threshold B and a decision threshold C. Okay. So I'm going to cut the chase a little short, and I'll show you what the true positive rates and the false positive rates are. And you can simply calculate it. You can see that when you're at B, the true positives are 2 divided by the false negatives, which are 4. Okay, these are the 4 cases. So it comes out to be 0.33. The false positive rate also increases. And where would this point be, this decision threshold on this graph? It should be TPR is 0.33. Okay, and it should be on this line here. And false positive rate is over here. So point B will be over here. We were talking about the threshold B, where we said that we have moved the decision threshold from A to B. And now what we've done is we've been able to see that the ROC curve, you can sort of see a curve forming. It's going from A to B. And now let's take a look at decision threshold C. We further move it down to the right. And you can see that I've calculated these values. You can double check them later on. The TPR comes out to be 0.66, and the FPR, the false positive rate, remains at 0.25. So you can see that point C will be somewhere over here, okay? And we already have point D. So basically the ROC curve essentially means that you change the decision threshold, you go from one end to the other, and as you're going, you plot the points, okay? So you can see if you eventually plot it, it's going to end up at D. And so this would be perhaps an approximation of how, for this particular example, the ROC curve would look like, okay? So you have some idea now what an ROC curve looks like. Let's keep looking at some further examples. So let's take a look at a linearly separable case, okay? And linearly separable, as you can see, is that you can simply draw a decision threshold, and that would separate all the rectangles from the triangles very nicely, okay? They aren't mixed up. So if you do the calculation of the true positive rate and the false positive rate, you can see that the true positive rate would simply be 6, and the false positive rate would simply be 4. So this is the perfect scenario. So if I were to plot this, where would this plot be? And can you guess what the curve would look like? Can somebody suggest how the curve would look like? And where would this particular point X be on this curve? So TPR is 1 and FPR is 0. Okay. So quite clearly, this is going to be over here. Is that clear? Now, given that one of these points is over here, and we already know that there's going to be a point here as well, and there's going to be a point here as well. Okay. So what do you think is going to be the form of the curve? Is it simply going to be going straight up? Is that your guess? Or could it actually go something like this as well? Can't go above it, but it might go something like this. So are both of these options possible?
Yes, sir, depending upon the other points.
So people think that the second option is also possible. So if I say this is the first line and this is the second line, so do people think that the second line with the double dashes is possible?
Yes, sir.
Okay, now let's analyze it. As you go from A, where you've actually put in the decision threshold over here, now you're sort of moving it in this particular case where it is linearly separable. Now, will at any point for it to go over here, the false positive rate has to become non-zero, okay? As you're going from here, from this point to this point, can the false positive rate at any point over here be non-zero? Can you actually have a triangle in here? Well, since it's linearly separable, it should be clear that there are no triangles over here in this region, right? And if there are no triangles in this region, then it should be quite clear that the false positive rate will always remain 0 as you move the decision threshold from this particular point to this point. I hope that's clear. Okay, so this is not going to be possible. Okay, it's going to move straight up, but the TPR is going to change. So if, for example, you had a decision threshold over here, what would your TPR be? Would it still be 0? It was 0 at this point, but as you went a little bit down, the TPR is going to be, for example, 2 upon 2 plus false negatives. So this is going to be 4. Okay, so the TPR is slowly going to go up from 0 all the way up till 1 as you move up here. And then as you move down, as you go beyond this, you should be able to figure out that this is not going to be possible. You're going to simply move along the straight line because your true positive rate is going to remain at 1. Okay, because all the rectangles are going to be on the left side. Okay, so just think that through. So what basically in the linearly separable data, the ROC curve is going to be very simple. It's going to be this red line. Okay, as you move your decision threshold from one extreme to the other extreme. Is this clear? Any questions up till this point? If not, let me move on. Okay, so here's another case. And now my question is, let's consider 2 points. Let's say this is one decision threshold. This is a hypothetical case. This is no longer the previous case. Now let's assume that there's a point X and a point Y. Now, which of these would you think is actually better than the other? Now assume that both of them have the same TPR rate. Only their FPR is changing, is different. So which is going to be actually better as a decision point? Where would you want to operate? Are people still in shock from the quiz?
Yes, sir.
Okay, still thinking about the quiz? Okay, focus over here because there are more quizzes and exams coming up.
Why is better?
So one gentleman thinks that Y is better. Anybody else who disagrees with this gentleman? Can you explain why Y would be better? You basically have the same true positive rate, but your false positive rate is higher. So I think Josefa has just said that X is better. Okay. So can somebody explain why X is better? It should be fairly straightforward. You can see that X, both of them have the same both of them have the same true positive rate. So true positive is something which you want to have. Okay. False positive rate is something you don't want to have. Okay. So ideally, as I said, in the linearly separable case, you want to operate over here. Why? Because your false positive rate is 0, okay, and your true positive rate is 1, which means you have absolutely you've done a great classification job. Okay, so you want to minimize the false positive rate and you want to maximize the true positive rate. So here you can see that X has the same true positive rate, but here Y is actually inferior to X because they're more the false positivity has actually increased. Okay, so X is actually better in this case. Okay, so if you've understood this, yeah.
Basically, X will give us more area, right?
Sorry, speak up a little bit.
Basically, X will give us more area.
X will give you more what?
Area under the curve.
Yes, yes. So I haven't come under the area under the curve, but I did mention earlier. No. You're confusing something. So X is an individual operating point. Now, interestingly, you might ask yourself, why is this called a receiver operating curve? Okay. Maybe writing ROC curve again is an overkill. Receiver operating curve, you might ask, what is a receiver? Okay, but this simply has some military history. It used to be used, it has military background where it was applied to signal receivers by the military, and that's why it's called a receiver operating curve. But the interesting part is that it is an operating curve. In other words, as you're moving from point to point, it basically says where should you actually have your decision threshold. So if you're actually trying to decide on a classification algorithm, you might have a decision threshold which operates at any point, at any one of these points. Okay, that's sort of your choice, and each one of these points is actually a decision point for you. So clearly, these two extremes are not very useful. Why? Because over here, your true positive rate is 0, and here your false positive rate is 1. Okay, so you don't really want to operate in one of these two positions. So area on the curve is not really relevant right now because you're simply looking at individual points. So when you're looking at X versus Y, you can't say that X is better because the area under the curve is better, because we're not really looking at the area yet. But you might say that X is better because at this particular operating point, your true positive rate is better, is the same as Y, which means you're doing equally good in terms of true positive rate, but your false positive rate is lower at X. Okay, and so you're not doing as bad. So okay, so this is a measure of goodness. All right, and this is, you can say this is a measure of, you might say, badness, if that word exists. Okay, so obviously if you can operate as well over here and not have any bad features, so this would be preferred. Okay, so is that clear? And does that answer your question about area under the curve?
Yes, sir.
Okay, so now if you understood these two operating points, we basically say which would be a better operating point, X or Y. The next question is, now let's take a look at algorithms. Okay, now we're not comparing individual points, but we're looking at entire algorithms. And we're saying that here's an algorithm A and here's an algorithm B. Okay, for example, algorithm A could be a decision tree, algorithm B could be, well, let's say, for example, this is a decision tree and this is a random forest, or it could be an artificial neural network, okay, or some other algorithm. And now you're trying to compare the two algorithms. So now, which algorithm can be considered to be better?
Okay.
So this should be fairly straightforward, and it comes out from your previous answer. So when you're comparing two algorithms, you would compare the entire curve. Okay, you not just look at individual point, but now you would compare the entire curve, and you would say that clearly algorithm A is better in almost all points. So there are lots of points which are actually superior. So if you look at this point, this is superior to this, right? Because clearly it has a higher TPR for about the same FPR. Similarly, this point is superior to any other point over here because it has, for the same FPR, it has a higher TPR. So the general way that you can sort of compare two algorithms, and you might have a case, in this case, it's kind of obvious that this algorithm is actually superior to this, simply because if you look at all of these points, they're actually superior. But if, for example, if you have two cases, let's say that you have case something like this, and another case which looks something like this, okay? So let's say this is algorithm C, and this is algorithm D, okay? Now which is actually superior? It's not quite obvious whether C is superior or D is superior, right? Because you can see that there are some points over here which there's a trade-off between these two, okay? Because the TPR over here is, if you compare the TPR over here, this has superior to TPR, but in terms of FPR, this also has a higher FPR, okay? So when you have situations like this is where you actually look at the area under the curve, okay? And there you can simply say that if you want to compare these two algorithms, we'll take a look at C and look at the entire area under the curve, okay? So this would be the area under the curve of C. And if you look at the algorithm D, this would be the area under the curve of algorithm D. And if you can simply calculate that, whichever area is higher would be the preferred algorithm, okay? So I hope this sort of summarizes the ROC curve, and this is practically used very frequently. And as you go forward in the next homework assignments, you will actually practically see this in it's used in competitions as well to determine the superiority or inferiority of algorithms. Okay, if there are no questions till this point, I'm going to go on to the next topic. Okay, so the next major topic is another algorithm, which is referred to as KNN algorithm, K nearest neighbor, or simply KNN algorithm. Okay, And this is another algorithm, which is a classification algorithm. And it's a machine learning algorithm. And it's also a supervised algorithm. Okay. And you can think of it as, so far we've already studied artificial neural networks. We've looked at decision trees. We've looked at random forests, right? So this will be yet another classification algorithm, but it will be more one of those traditional algorithms, okay? So just a review over here. If you recall, this was the example of the KNN that we had studied in one of our earlier lectures, where I had showed you that you have six data points, which are classified as cats versus dogs. And these were the cases which were classified as cats based on feature X1 versus X2. And these were the feature, based on the features, these were the categories which were classified as dogs because they had certain features which were quite different. Now, in the ANN example, we had said that if we train the neural network, you can find hopefully weights W1 and W2, which will give you an optimal solution. And this you could see is perhaps an optimal solution. And the equation for this line was X1 plus X2 is equal to 0. And that was this particular line, which was running right in the middle of these two areas, of these two categories, right? So the question would be that if you have a new point, and once you've done the training in your artificial neural network, if you've got a new point, let's say at 4, 8, okay, this is your point 4, 8, how would you decide whether it should be category 0 or should it be a category 1? Well, hopefully you would simply say, well, let's try to put it into the, you would evaluate this based on the F and the phi values, okay? You would enter the new values 4 and 8 over here, and you would calculate the F value and the phi value, and you would simply say if Y is coming out to be a 0 or a 1, then if it's a 0, then it's a cat. If it's a 1, it would be classified as a dog, okay? So let's just do the math. We would take X1 plus X2 minus 10, which is the equation of the line that we had found, and it comes out to be plus 2. And then we simply say that phi is a step function. So phi of 2 is clearly a 1, in which case the class would be that of a dog, okay? So this is how the ANN algorithm would work. And this is something that was somewhat of a recall, okay, a review of what we've already done. Now let's take a look at the KNN algorithm. It operates slightly differently, quite differently in fact. And the basic idea behind this is that there's a K, which is an integer, and it's generally an odd number. And the idea is that we'll assume that the existing data has already been classified using supervised learning. And that's why this is called a supervised learning algorithm, okay? So these are the points which have already been classified between 0 and 1 using supervised learning, okay? These are all the zeros and these are all the ones. And now you've got a new point. This is again, let's say 4 and 8 over here. And what you're going to do is based on the value of K. So the value of K is generally specified as part of the algorithm. So let's say that we pick the simplest value of K, which is K is equal to 1. So what we're going to do is we're going to select the K nearest points and decide the category based on the majority, okay? So here, if K is equal to 1, we're going to draw expanding circles around the new item that we're trying to classify until we come across the first item, which is nearest to it. So as we can see that the item which is 5 and 10, which has values of 5 and 10, is the nearest, and that's sort of visible as well. So this is the one which is the closest as opposed to the other points which seem to be fairly further away, okay? So because 5 5, 10, this particular point is a 1 category, hence X is going to be classified as a 1. Okay, so is this, so far is this clear? And if this is clear, then I'm going to show you another example.
Sir?
Yeah.
How did we calculate the big X?
Yeah, sorry, go ahead.
How did we calculate the big X?
How did we get what?
X.
Okay, so all I'm saying is that X is an unknown. Okay, so as in the earlier case, we said that if you have a new item X, okay, so this is a new item which needs to be classified. All right, so this is a new item which could appear anywhere over here or anywhere on this particular feature matrix, feature graph. And the question is X, is this new value, should it be classified as a 0 or it should be classified as a 1? Okay, and basically what we're saying is that we look at the nearest neighbor, and we're going to simply, in the case of k is equal to 1, we're going to look at the nearest neighbor, and if it happens to be a 1, we'll make X's category as 1. If it happens to be, for example, if X was over here, then clearly this particular neighbor would be the nearest, right? And this would be a 0, so we'd classify this value over here as a 0, okay? So it depends on who the nearest neighbor is. So if X is equal to 3, how would this work out? So let's take a look at some examples where now we're looking at different values of K, okay? So I've already done K is equal to 1, and we found that if you look at K is equal to 1, let's say this is a new point y1, I'm not calling it an X anymore. Let's say this y1 is the point that we're trying to figure out what classification should it be. So this is 7, 10. Okay, so this is your new item, which is y1, which is a 7, 10. Okay, so a 7 over here and a 10 over here. And so the question is, if you're looking at, for k is equal to 1, you would draw a circle, and eventually you would find that this circle, this is the nearest neighbor. And the way you would actually do it is you would, for each one of these points, if you look at the actual mathematical calculations, for each one of these points, you'd actually have to calculate the distance, okay? And so what you would do is you have 5, 10 is 1 coordinates, okay? 5 and 10. This is the coordinates for 5, 10. And this is the coordinates for 7, 10. So in this case, it's quite clear that the distance is simply the distance on the horizontal axis, which is 7 minus 5, which is 2. Okay. So this is the nearest neighbor. But as we increase k from k is equal to 1 to k is equal to 3, remember this, we're only going to use odd values. So when you go to k is equal to 3, you can see that the next two neighbors are 6 and 4. Okay, 6 has the distance, which 6 is 10, 10. This is 6, which is 10, 10, and this has a distance of 3. You can see that the distance over here is 3. And then the next one is 10, 5, point number 4 over here. And that has a distance which is slightly tricky to calculate. Does anybody remember the equation to be able to figure out in 2 dimensions the distance between 2 points? How did I get 5.83?
Under root.
Yeah, so there's an under root, and you do x1 minus x2 the whole squared plus y1 minus y2 the whole squared. Okay, so this is something that you all remember. So that's how you figure out the distance between these 2 points, and you can, once you've calculated this, you find that this is 5.83. So let's say that we had to use k is equal to 3. If you think about the complexity of this algorithm, it would first have to figure out the distances of all the existing points. So right now, we have a total of 6 points, right? Remember the 3 points that we had in this classification and the other 3 points. So for all of those 6 points, it would have to find out its distance from the new item. Okay, so every time you want to classify a new item, you would have to do, if there are n previous items, you would have to do n calculations, n iterations. And for each one of them, you would have to find out the distance, and then you would sort of sort them out. And you'd figure out, if you're doing k is equal to 3, you would find out which are the 3 nearest neighbor. You don't have to sort all of them, but you'd have to sort out the first 3. If you're using k is equal to 5, you would sort out the first 5. Okay, and then you would say, well, if you're doing k is equal to 3, the nearest neighbors are classified all green ones. So these are all the ones which were classified as a 1. So it would still be classified as a 1. Here it was also classified as a 1. If you look at k is equal to 5, this would also be classified as a 1. Why? Because you have, in this case, you've got 1, 2, 3 neighbors which are classified as 1, but you also have 2 neighbors which are classified as zeros. Okay, so there you would actually have a voting. You would say, well, there are 3 which are 1s and 2 which are zeros. So 3 versus 2. So you're going to pick the 3 case, and these are the ones which are classified as 1. The 2 were classified as 0. So you're going to pick 1 as your classification for the new item Y1.
So what if they are equal?
So what if they're what? Sorry?
They're equal, the equal number of.
Okay, so the reason why they're not going to be equal, why, is because we're picking k to be an odd number. Okay, which is why we're not making k is equal to an even number. If k was even, if k is odd, then you can clearly see if it's a binary classification, then it's going to favor one or the other class. Okay, so I hope that answers that question. Now the question is, will this always work, or will this always give you best results? And can somebody think of an example where it may not give you a good result? So let's take a look at this example. Here is, now in the earlier cases, remember I picked y somewhere over here. So this was y1 over here, and the other example that I picked was also over here, the first example. But now instead of using k is equal to 1, as k increases, what do you think the results are going to look like? Okay, now what about k is equal to 3 in this case? Which are the 3 nearest points over here? So the points are 1, they're labeled 1, 2, 3, 4, 5, and 6. So which are the 3 nearest neighbors of x, do you think? Without doing a mathematical calculation.
5,
This
3.
is going to be 5, that's definitely the nearest. Then which is the second nearest?
3.
Yeah, 3 is going to be the second nearest. And which is the third nearest?
6.
It's hard to say, but actually if you do the calculations, it's actually number 2 is the third nearest. Okay, so in this case, if these are the 3 nearest neighbors, y1 is going to be classified as a 0 or a 1. Because 2 of these neighbors are actually classified earlier as 0, it's going to be classified as a 0. Okay, it's going to be 2 versus 1 over here. So even though visually we can see that the line earlier was somewhere over here, and you can see that x is actually closer to these points 4, 5, and 6, but KNN has, in this case, for k is equal to 3, come up with the wrong classification, which you might say is the wrong classification, right? And you can see that over here. So I've drawn the circle for k is equal to 3, and you can see that this point, and these are the nearest. Okay. So this tells you some of the problems with the KNN classification algorithm as well. Okay, but it's still a very popular algorithm. Now let's take a look at some other issues with the KNN algorithm. Now let's take a look at the specific case of y2. So I've already shown you for k is equal to 3, it comes up with 0. But even if you look at k is equal to 5, unfortunately, in this case, even for k is equal to 5, point number 6, these three, 5 is the closest. Then there is 3 and 2, okay, 3 and 2. And then the next one is number 1, okay, so this is still closest. And after that is point number 6, okay. And this point here is still the furthest away, okay. So even if k is equal to 5, you get a misclassification of classifying it as 0, okay. So you can see that this is just another example to show you that KNN will not always give you the best results. The next question in KNN that you might want to ask is, how do you actually determine the value of k? Okay, so now looking at the examples, can somebody suggest how do we actually, for a real case, so suppose you have a bunch of data, okay, you've got a bunch of data, and now you need to determine what value of k should I select? And then the next question will also be, what if I make k very small or if I make k very large? What do you think are the pros and cons in this basic discussion as to what should be the value of k? Any thoughts? So think about what the problem is. The problem is that you've got a bunch of data. Okay, so let's say these are crosses and circles, and we're trying to classify them, and there's a whole bunch of these. Okay, there might be some outliers as well. All right. And now we've already labeled all of these using some supervised learning. And now we have unknown. Okay, so let's say the unknown is over here. Or even before we have the unknown, we need to determine what should be the optimal value of k, or what should be a good value of k to choose from. Okay, so think about this as, you know, these are your friends, these may be your enemies, and how do you want to be classified? Which one do you want to be classified as? Okay, do you want to be in the enemy camp, or do you want to be in the friends camp? So how many friends should you consider, or how many enemies should you consider before you decide your fate? Any thoughts on that?
So it depends upon the number of entries we have in a data.
Yeah, so that's a good thought. So if you have, for example, a large number of data points, okay, so you may want to make k relatively large, because then you're essentially saying that you have a lot of data, okay. And if you have already have a lot of data, you might want to pick a relatively large number, or even a small number. But because you have a lot of data points, you may actually have, you know, you may, even with a small circle, you may have a large value of k. So that's a very good suggestion. Now let's take the extreme case. What if you make k very small? Okay. But before I get to that, here is a suggestion that has been used, okay? And this is one of the techniques that's been used. So what we could do is we test a set of random data, okay, for various values of k is equal to 1, 2, 3, 1, 3, 5, and so on, and see how accurately they're classified, okay? Now you can see how powerful this particular suggestion is that in order to be able to determine what the value of k is, what you could do is you could partition your data. So let's say you have 100 data points, okay? You take 80 of those to be your training, and you take 20% of them to be your test cases, okay? Now you already have the labels for these 20. So what you're going to do is, for these 20 which are randomly selected, you look at various values of k, okay? And you look at k is equal to, let's say 1, 3, 5, and so on. And then you figure out whether for k is equal to 1, was it correctly classifying it? Was it, what was the result? Was it correct, or was it wrong? Okay. If let's say it is wrong, then you might want to move to k is equal to 3. okay, for majority of the cases. So let's say you testing 20, and for here you found out that 15 of them are wrongly classified and 5 of them are correctly classified. So that sort of says that, k is equal to 1 doesn't seem to be a very good algorithm. So we move to k is equal to 3. Let's say for k is equal to 3, we have 15 correctly classified and 5 incorrectly classified. So this seems very good. Now, when you go to k is equal to 5, you again, let's say you go to 5 versus 15. Okay, so now you realize that for when k is becoming 5, the results are not very good. So clearly, this is the optimal solution. Okay, for this particular example, that when you make k is equal to 3, you have the best results. Okay, 15 of them are being correctly classified, only 5 are being misclassified. So this is one way that you could actually figure out what is the optimal value of k. Okay, test it out on test data, on partition your data set and test it out on that. Now, going back to the issue, what if k is too small or too large? What do you think are the trade-offs? Okay, so if you think about the previous examples, if you make k is equal to very small or very large, if you have different types of data sets, when would one become a problem versus the other? So let's focus on, let's say k is equal to too small. So if k is equal to too small, what kinds of problems do you think you could foresee?